Lecture J4. Now we are moving from the estimation of absolute performance, where we measure a particular value coming out of a sim and we evaluate its absolute value. So we're not comparing it to anything. We're actually saying that this is a good estimate of, for example, the number of people that are held in line for longer than we want them to be held in line for. So when we trust that this is a good estimate of the actual number of people who experience this bad performance. Now we're moving that to estimation of relative performance, which is often more useful because simulations aren't as always a perfect match for reality, but they might be a nice qualitative match. And so it may be that your simulation doesn't give you a number which would match exactly what you would get out of the real system. But if you modify the sim in a particular way and it improves the performance in the simulation environment, then we may have high confidence that you'll get similar improvements in the real system. So if we have two ways of comparing two different sims, we may be able to make a more useful inference than actually trying to estimate a real parameter from a single sim. So hopefully that will become more clear here in a second. But let's just make sure that we're all on the same page about where we've come from here. So we have now moved away from point estimates to interval estimates. And so in the past, we would just calculate a sample mean, and now we are trying to then capture, instead of reporting a mean to our customers or our clients, we are now reporting an interval which somehow captures how confident we are about where the mean is. And so we're not trying to then say we definitely think this is the mean. What we're definitely saying that we think the mean is in this interval. And so we could try to communicate that with a series of t-tests, but instead we just take the t-test and we collapse it down into this thing called a confidence interval. And so a confidence interval, as I've said before, is inside the interval. Those are all of the hypotheses that would not be rejected by a t-test, and outside the interval, those are all the hypotheses that would be rejected by a t-test. That's one way to interpret it. If you go to other classes, some other people might say that a 95% confidence interval is if you were to take the data 100 times, and then for each time you took the data, you generated a confidence interval giving you 100 confidence intervals, then the true mean would be in 95 of those 100 confidence intervals. That was another way to interpret what a confidence interval is. Whichever one is more comfortable to you, that's fine, they're equivalent. And so the way we derive the confidence interval is just by doing t-tests. And so on the left-hand side of this top row here, I've got the condition for rejecting a hypothesis in a t-test. So I've taken some data and I've calculated this x bar, which is my estimate of the mean. If I were to take the same amount of data again, I would get a different mean. And so if I keep doing that, take the same amount of data again, I would get a different mean. And then that mean would form a distribution. It would be a little bell curve. And then that bell curve would have this variance down here at the bottom. And so what I'm doing is I'm subtracting my hypothetical mean. And so if I assume, so in a t-test, we assume that the hypothesis is normally distributed, and we assume that the data are normally distributed. And the hidden assumption that you may have forgotten or it was maybe never emphasized is we also assume that both the hypothetical distribution and the actual distribution have the same standard deviation. And in the case of an estimator, the standard deviation of the estimator of the mean is this denominator here. That's what we call it, the standard error of the mean, or the SEM. So referring to this as the SEM, you're going to see this come up later in the lecture. And so we just need to become comfortable with the thing in the denominator of the t-test, which also shows up in the confidence interval, is the so-called standard error of the mean. It's the standard deviation of the estimator. If you were to take estimators over and over and over again, if I were to keep generating estimates of the sample mean, so I take 10 data from the simulation, I generate a sample mean. I take another 10 data points from the simulation, I generate another sample mean. If I were to do that over and over and over again so that I get 100 sample means, and then I took a histogram of those sample means, it would look pretty much bell-shaped, and the standard deviation of that bell shape would be this denominator down here. So what the t-test does is it calculates a z-score, assuming that the hypothetical distribution is centered on theta, and our sample is out here at x bar, and so it's saying that if the hypothetical distribution of the estimator would be centered on theta with this standard deviation, the s over square root of n, then the z-score is going to end up giving us effectively a mapping to the likelihood that the data actually came from this distribution. And so that's kind of how a t-test works. So that's why this looks like a z-score. It is really, it's an absolute value of a z-score. And so, for low numbers of samples, then the distribution we compare it to is not actually the standard normal, it is the t. But that's why if you take a high number of samples and you look in the back of the book, you'll notice that the critical t values go to critical z values. And so the t distribution becomes the standard normal distribution when you have high degrees of freedom, or when you used a high number of samples to do your estimates. And so, back in the old days before the t-test, this all you had was effectively a z-test. But the t-test allowed you to take your z-test intuition and extend it to small numbers of samples. And so that's how a t-test works. Just as a reminder of how t-test works, if you didn't get any of that conceptual stuff, but you understand the formula, that's okay with me for now. And this here is the formula for how you would reject a hypothesis. You reject theta if this thing is true. With a little bit of algebraic rearrangement, this statement on the left is identical. That's what this symbol means, if and only if. So it's identical to this statement over here. So if theta is such that the thing on the left is true, that can only happen if and only if theta is outside this range, where I have this h is this half-width, which I've introduced down here, which is, again, that standard error of the mean scaled by this critical t value. And so these are all of the hypotheses that would be rejected. If I can't reject them, then they're inside the interval. So that's what I mean by that's what a confidence interval is. It's just the number of these it is the hypotheses that are either definitely rejected are outside, and definitely not rejected are inside. And so you could imagine that I might ask you about a particular hypothesis and what you would guess about the p-value that corresponded to that hypothesis and these data. And so if I give you a bunch of data and you calculate a confidence interval, and then I ask you about a particular hypothesis, and I say, what would be the p-value for these data and this hypothesis? If the hypothesis falls inside that confidence interval, you know that that p-value is less than alpha. If the hypothesis is, if the hypothesis is outside the confidence interval, then you know that the p-value is less than alpha. If the hypothesis is inside the confidence interval, then you know the p-value is greater than alpha. So if you've drawn a confidence interval and I ask you about hypotheses, you can compare the hypotheses to the confidence interval, and without doing any other calculations, you at least know whether it's less than alpha or greater than alpha, or greater than or equal to alpha. So that's an important thing there, is that if I give you a confidence interval, you should be able to estimate the p-value, at least in terms of alpha. So if you think about it, then what's the relationship between alpha and the half-width? Well, we know that if I set alpha equal to 0, then I'm not going to reject any hypotheses. Well, if I don't reject any hypotheses, then that means everything's inside the confidence interval, because the confidence interval are all the hypotheses that I don't reject. So if alpha becomes small, the half-width becomes very large. On the flip side of that, if alpha becomes very large, so if alpha is equal to 1, I reject all hypotheses. Well, the only way I can reject all hypotheses is if the confidence interval collapses onto the mean. Um, so that's basically all hypotheses. So in the limiting case where alpha is equal to 1, h is equal to 0. In the limiting case where alpha is equal to 0, h is equal to infinity. Okay, so that was the one sample case. But we can also take our intuition about confidence intervals and start to do something that looks a lot like a two-sample t-test. And in many cases will actually allow us to infer what the answer to a two-sample t-test would be if we actually had done the two-sample t-test. And this is going to be very important because as we move into estimating relative performance, we're going to move into doing a lot of two-sample tests. So in a two-sample t-test, we assume that x and y are normally distributed, and in the null hypothesis, we are assuming that the mean of x is the same as the mean of y, and we are evaluating whether that is actually true in the t-test. And so do we reject the null and assume that they actually have different means? So in order for us to do that with confidence intervals, we can just calculate a confidence interval for x where we have a half-width for x. And so the half-width for x corresponds to effectively the variance in x. And then, of course, x bar is the mean of x. So this effectively is a way to characterize the mean and variance that we infer in the underlying distribution of x based on the little bit of data that we've taken about x. And similarly for y, if we've taken some data from y, we can calculate a sample mean for y, and we can calculate a sample standard deviation, and then that gives us an estimate of this confidence interval for y. And so individually, these confidence intervals are inferences on the mean of the actual x and the mean of the actual y. These are confidence intervals are one sample tests. Again, everything inside the x confidence interval are x hypotheses we cannot reject, and everything inside the y are y hypotheses we cannot reject. And so that's just there for one sample. But in the particular case that these one sample confidence intervals have no intersection. So that's what this means here. This is, this interval intersected with this interval is the empty set. That's what this notation means here. So if there is no overlap between those confidence intervals, then we can actually assume, or we can actually then infer that the mean of x is different than the true mean of y. So we've actually done a two-sample t-test and reached significance, our significance level of alpha, without actually doing any of the calculations of a two-sample t-test. And so there's no if and only if here. So notice that this is I'm purely implying in one direction. If you have a one-sample confidence interval and a one-sample confidence interval, so in other words, a confidence interval, if you have a confidence interval x and it does not overlap with the confidence interval y, then we can assume that if we were to have done the true two-sample t-test, then we would have gotten a p-value less than alpha, and we would have concluded that we would reject the hypothesis that these two are equal. Now, if it is the case that there actually is intersection, so here is the confidence interval for x intersected with the confidence interval for y, and you do not get an empty set, that means that they do overlap, there's absolutely nothing that we can conclude. So this confidence intervals are only useful in the two-sample case when there is no overlap. Whenever there's overlap, there's nothing we can do. So if they overlap, you have to do the real two-sample t-test. So here's a graphical example of this. This is different than the example I showed in the previous lecture. We have two HIV detection methods here, and they're on the y-axis. These are days until HIV detection, and they're trying to detect if detection method B is truly faster than detection method A. And initially you might stare at this, and if you looked at the means alone, I mean, this mean is lower. So that might mean something. But if we actually then look at the confidence intervals, then we see that the confidence intervals intersect. And so because the confidence intervals intersect, we have to do a t-test, and we end up finding that the t-test for this one is less than 0.05. And so because it is less than 0.05, then we actually conclude that there is a significant difference here. So we keep getting tugged in all these different ways. And so initially we look at this, and if we looked at just the means, it looks like there's a difference. But then you put the confidence intervals up there, and because the confidence intervals overlap, you might conclude that that they must be the same. But if we actually do the two-sample t-test, like up here, then we find that you actually get a p-value that's less than 0.05. And so even though the confidence intervals overlap, the p-value is less than 0.05. So we end up concluding that actually detection method B is significantly different than detection method A in terms of days until the infection. So we conclude that maybe detection method B is better because it's slightly faster to this level of significance. So the key point here, this is a confidence interval in a performance metric. This is a confidence interval in a performance metric. If they did not overlap, we wouldn't have to do the t-test, and we could assume that B was better than A. But because they overlap, we cannot conclude anything. So you might be tempted to conclude that B is now the same as A, but when we actually do the t-test, we find out that B truly is different than A. All right, so those were confidence intervals. So I'm going to pause right now, and so go back to Canvas and answer some questions related to what you just heard about confidence intervals, and then we'll get back into recapping the terminating and steady state before we go on to relative performance, where we'll definitely use those two samples.